My name is Louis Turner, Louis-Turner. I'm a metallurgical engineer, graduated in 1941 from the Colorado School of Mines. I was working in Denver Ordnance Plant when I was asked if I would go to Chicago by DuPont. They wouldn't tell me what for, what I was going to do, or anything like that, but it sounded like a very exciting job. Besides that, I was working with a DuPont in the Denver Ordnance Plant, and he encouraged me to get into it. He said, DuPont's a great company. So I went back to Chicago in September of 1943 and reported to Dr. Al Greninger, and he sent me over to the dairy, which was the code name for this place where we were trying to learn how to can fuel elements. Big problem there was to provide a bonding agent that would thermally conduct the heat generated by the nuclear reaction. It would conduct the heat from the uranium through the aluminum into the water that was cooling it. And we had great difficulty there. We had a whiz-bang, we had other instruments trying to learn how to. There was a dozen or so metallurgical engineers like myself. We were really gophers trying to learn how to do this. None of us knew a lot about uranium. And finally, a eutectic compound, eutectic being a low melting point of silicon and aluminum. Of aluminum and silicon, a eutectic that melted at less than the melting point of aluminum. And it could be used to provide the thermal conductivity. But we were never really successful in cleaning the uranium because it was very corrosive. It reacted to the air. You had to be very careful how you cleaned it. But at Hanford, they discovered the right way to do this, and so we were all told, that's it. We don't need you guys here anymore. We got other jobs for you. So they sent me down to Oak Ridge to learn how to be a health instrument person. I didn't know much about radiation at the time. It's very interesting because I think Cleo Patterson was my supervisor down there. I met Carl Morgan, and they were all very knowledgeable in radiation protection. And so we worked around the reactor there at X-10, and I was there for 3 months when I was told, we need you out at Hanford. The B reactor has gone critical. Again, I still didn't know where Hanford was. And the PR people there from DuPont, of course, said it was someplace south of Spokane. But it's in the Evergreen State. Now, I make that comment very knowledgeably because I expected an Evergreen State when I came out here. Anyway, we came by train from Oak Ridge to Wallula, which is now underwater, and then by Army bus to the Trenchant Quarters, which is now the Red Lion. And went to work the next day out in the area, which I learned was pretty much of a desert area. After a preliminary training period with Dr. Parker, Dr. Gammertsfelder, Jack Healy put 4 of us into a car, a Blue Goose, and our job was to go around the area on an 8-hour, 24-hour shift to make sure that the reactor didn't blow up. It was during this period that I learned a lot more about radiation and a lot more about the desert. So we would leave Richland on our shift, drive out to the area. I would drive it back and pick up the next fellow that was to take my place, and then he would take me home, and then he would go out in the area. And we did that for about 2 or 3 months. We never did find, of course, the B reactor never did explode or anything. We never detected any radiation. The instrument was a Beckman, which was about, 7 or 8 inches long and about 6 inches high, and it weighed about, 5 pounds or so. It could detect radiation to about 1 MR per hour, milliröntgen per hour. After that, I guess it was in December that year that they started the T-plant, and I was assigned to go over and help them set up monitoring devices for during the dissolution. We built some ionization chambers in an old badge house there and stuck them out in the field. And the first dissolution that occurred, there was an inversion, and the radiation came down, discharged those monitors so fast we couldn't even measure them. After that, I was asked to be part of Health Instruments that was doing site survey. I had a crew of about 4 or 5 people that every morning we would go to work. We would come out over the hill there and find out whether they had dissolved during the night, call up the operation, ask them how many curies of iodine had been discharged, and I would send a crew out in their Jeeps. We would collect sagebrush from here all over the area, and they would then bring it back to the laboratory for counting, and isodose maps were made showing what the radiation involved was during those irradiations, dissolutions, excuse me.
What were some of the things that you learned from your work in looking at the radioactive exposures to the environment?
Well, I can't say what I learned except how to handle instruments, and that instruments were always improving. The measurements were getting more accurate.
Or I should ask the question another way. What did you find from your studies? Were there levels in the sagebrush? Did it depend on?
Yes. Radiation values could produce a very good trace in the direction of the wind. Now remember, the people could not dissolve if it was raining or snowing. They could not dissolve if the weather conditions were not right. There was a meteorological tower out there that gave the operators a go-ahead if conditions were correct for dissolution. That was, I think, a 200-foot stack that the gases would come out. And they were we could usually detect them when we came to work in the morning if they had processed fuel at night.
What was the primary substance that was released during the dissolution process at T-plant?
Well, as far as I know, it was mostly iodine-131. That was the one that we usually measured. It had an 8-day half-life, and we could record it and relate it to make these isodoses. There was a period of time later on when some of the corrosion products from some of the facilities would also come out in the effluent, and we would find particles inside these fenced areas that was a lot more radioactive. Normally the material, the iodine on the material that we would pick up in the field was very small.
And you said that one of the precautions that DuPont took was only to run this process, the dissolution process or the chemical separation plant, when meteorological conditions were favorable.
That's correct.
That's correct. What did they not anticipate about these inversions? I guess is there something that that was unanticipated by the way the stack, wasn't that it's supposed to disperse it at very high level, and then there were some...
Well, I think meteorological changes occurred sometimes after they'd started and there was no way of stopping the operation. And I think that that may have happened. I don't know that it did. Most of the radiation that I detected was inside the fenced area, although we would detect, we would produce these isodose charts that would go towards Richland and towards the east because the prevailing wind was that direction.
So how far away did you measure detectable quantities of these substances?
Well, we took samples as far south as the Dalles. We went as far west as Yakima. We went far east as, far north as Moses Lake. And it would tail off. You would get an isodose chart that would tail off as you went farther and farther away from the plant.
What visible signs were there that the batch had been run or was running?
Well, when we would come to work in the morning, we could see the brown smoke from the nitrous oxide that was coming out of the stack. And you could also smell it. That was the tail end. Excuse me.
Excuse me. Did they operate just at night then?
Normally, they just dissolved at night because that was the most favorable meteorological conditions out here.
And if you saw these plumes in the day, they were sort of the
Tail end. Tail end of the dissolution, yes.
Would you say, it's curious, would you say that, really the science of environmental monitoring might have been birthed at Hanford? I mean, this was really the first time anybody measured radiation in the atmosphere, in the area.
That's probably true.
Could you talk about that? I mean,
Well, I'm not an expert in that. The amount of instrument development work was going on continuously. There was a group in the 300 area. Maybe one of these other fellows that are here this morning can talk a little bit about that. That were developing instruments all the time, and instruments. Well, as you know today, you're measuring picocuries. So it's been a continuous development of the measurement of radiation as a result of this effort.
Were there guidelines with respect to exposures, above which levels, let's say you found some close to where there was some population living, that you would then warn the population? Were there policies and procedures in place?
Yes, we reported all this into, if there was any danger to anybody, we would have known. Now, there were obviously, and I don't know what those are, I really don't. I know what my tolerances were. They were developed so much per week, per month, per year, that I couldn't exceed that amount. And we wore film badges and finger badges and other apparatus at times to detect. We always had a special work permit prepared by a monitor to go into a more hazardous area, let us say. I always like this we worry about fire, but we can protect ourselves. We worry about water, but we can protect ourselves. We worry about automobiles, but we can protect ourselves. But radiation, we can't see it. So we have to have some kind of an instrumentation that tells us when we've had our quotes, what we figured was the daily tolerance to human body. And that was developed very early on. Now, I don't know what it is today. I'm sure it's changed. As I recall, we had, what, 250 MR per week? Something like that.
And just to help the audiences understand what 250 MR per week translates to in terms of X-ray that they might have.
Gee, I'm afraid I can't do that.
That's all right.
I'm looking at it, I'm thinking of an X-ray technician that wears a lead apron and all that sort of thing. I can remember a job that I had that I would receive my total daily tolerance in something like a minute. But I had to put on protective clothing, no radiation protection. I worked on the job for a minute and I got out.
So all in all, how would you describe the kind of safety?
Okay, let's stop there. I mean, you know, okay, you've got a nuclear facility, it's the middle of the war, you have to hurry up. And yet somebody said,
Dr. Parker and Carl Morgan were the leading exponents, as far as I know, of people that knew that we had better have special work permits, that we'd better set some kind of a tolerance. We at least knew something about X-rays, didn't we? I think at that time. And we knew that there were people, some of the people at Oak Ridge who had burns on their hands from handling solutions of radioactive materials. They knew some kind of tolerances. So that's all I know about it right now, is that we did have a weekly, monthly, annual tolerance. And then when I finished up my job here, for example, I was put on a continuous examination type thing. And in fact, for years, we had to go in every year for a whole body radiation. I also ought to explain that during this period, we all had a 24-hour period where we collected our urine. The urine was analyzed. This was for everybody that worked out here. So everybody was aware that this was hazardous and that we'd better know more about it. And I think there ought to be a lot of data available.
so do you think that came from DuPont? Because DuPont was a munitions manufacturer and they were incredibly safety conscious as a corporate culture.
It could be. I don't know whether it originated there. I don't know whether Parker and Morgan were, I know Morgan didn't work for DuPont. I don't know who he worked for down there at Oak Ridge. I forget the name of the company that ran the X-10. But these physics-type people were well aware of the effect of radiation. It may go back to the Curies and Rutherfords. I don't know. Because when the Curies first discovered radiation coming from a blob, you know, they probably had some burns on their hands resulting from the handling radiation. And from that, a whole culture of radiation exposures was determined. If you ask me what the value is today for you or me or somebody else, it might be determined by weight. I don't know.
I think Michelle can answer that question.
Great.
She talks about both.
Yeah. Well, it's always good to have two people because
Yep.
this is an
Yeah, okay.
Can you tell us more about your work at Hanford and after the assignment on the health, or any more about the health instrument work that you did that you think would help people understand what it was like, the level of concern and.
Well, I think I could conclude by saying that we were very cognizant that radiation was a hazard that had to be measured, and that one of the things that was cited to us was the experience of Trail, British Columbia. There was a smelter up there that had produced quite a bit of fume from their smelter work, and they had ruined some orchards as a result of their fume. And we were all asked to please review that literature as a comparison with the effect of irradiation. Now, we didn't expect it would happen that way, but to make sure that we were aware that we should be careful how we measured it. So that's why we made these isodose plots and so forth. And while the work is going on today, we're still sampling the Columbia River. There's still an environmental survey out here that's doing that all the time. Wells were dug, samples are taken, radiation measurements are made all the time. And measurements, as I indicated before, are getting to be more sophisticated now, more detailed. You can pick out the isotopes, you can pick out the energy ratios, you can do all that sort of thing. We couldn't do that then. We were measuring, quotes, radiation.
What about the water monitoring? You mentioned the disposal of some of the water, and some of that went on the ground and some of it.
Well,
how does that work?
Well, the samples of water were taken, evaporated, and counted, and results tabulated as to determine what was happening. We don't know how much absorption or adsorption that the soil would take up any solutions. Might be quite a bit. I don't know. I don't have access to any of those records.
But there were other crews that were monitoring all
Yes.
these wells and the river water and.
Yes, there were people going out in boats and had sample arrangements that take different depths. Samples were taken all up and down the Columbia River, Yakima River, Snake River, I think.
And also samples of fish tissue and.
Yes, at one of the reactors here, I think it was D reactor, one of these other fellows can check this, they had a fish pond. They had a fish ladder inside that took the effluent from the reactor. The fish lived in that, and results were obtained. I think Battelle did that work.
Tell us about your living conditions. You say you lived in the Red Lion. What was
The transit
and
quarters.
The place, right, the transit quarters. Tell us about those.
Well, it was just a place to live while you're waiting for a house. I was married. I had one child, one on the way. And because of my position, I was entitled to an A house. And you all know about the alphabet houses. And when I say A house, why, everybody here in the room, or most everybody in Richland, would know that that's a 3-bedroom, 2-story duplex with a quarter of a basement. We didn't have any air conditioning. When we got up here, we didn't have any washing facilities, and here I had a baby to take care of. C.C. Anderson's was the only big store in town, and so we got on the list down there, and the joy of my wife's life at that time was to get an easy washer. Old hat right today. But anyway, that's what living conditions were like. I still couldn't tell my wife what I did until 45.
So was she surprised to
And
find
then
out?
she was surprised. In fact, she said, "Do you know what you're doing?" I said, "Sure." I had known for some time that what we were doing.
Did you know because someone had told you, or you just figured it out?
No, we were told in Chicago. Greninger told us what we were up to, what we were about, why we were doing, working with the uranium, and why we were trying to achieve some sort of superiority in getting it first, and why we were in such a haste to get it.
Did you didn't tell your wife, and your colleagues presumably knew, but did many other people know who are working on the plan?
I haven't any idea, but I'm guessing there's at least 1,000 people knew. I'm not sure. But most of us at Chicago had a pretty good inkling of what was going on, besides being told. I don't know how many people around Chicago knew what was going on at Stagfield and at the dairy. I would be surprised seeing all those educated people walking in and out of that place that they wouldn't suspect something.
7 minutes left on this tape.
7 minutes? Okay, well, after you worked on the health instrument work, tell us about what your next assignment was.
Okay, in 1946, GE came into the plant here. Dr. Parker called me in and he said, Lou, they've got an opportunity over there in metallurgy. Would you like that? He says, besides, you're not a health physics man anyway. And I approved of his candor, which was true. So I had a chance to go into radiometallurgy and metallurgy in the 300 area, and I reported to Dr. Ray Ward in the 3706 building. That was in 1946. And at that time we were trying to do some research. I didn't do much in the way of canning there or working with fuel elements. But then they started running into problems out at the reactors. They had leakers. And I was asked if I would kind of look into that since I had all this, quotes, health physics experience, unquote. So I said, sure, I'd be glad to. So we went out and organized a building out in back of Han 105B and 111B. And we started to get set up to examine radioactive materials, recognizing what the radiation problems were, developing remote control, remote handling as well as we could. We did a lot of material with 20-foot tongs, handling it hither and yon, examining it with telescopes and not much microscope work because you couldn't get that close to it. And at that same time, they were having a big problem over at one of the reactors, in that the graphite had caused the tubes to bend, or they weren't sure whether it was the tubes or whether it was the fuel element. So I was asked to please cut up a fuel element. So one of these fuel elements came out of the reactor. It was a little bit bent in the sense that it was hard to push out of a tube. And so we took it over to the 212 North area, which was between 200 and 100 area. It was a storage, interim storage. When fuel elements would come out before they were dissolved, they would be stored. So we took over this place and we built a cutoff machine out in the desert, surrounded it with lead, put this fuel element into it with tongs, cut it, wafers off of it, etched it, photographed it, discovered it, nothing. Just it was hard to handle. It was difficult to handle. But it received some acclaim that we had done it. And then from there on, why, GE entitled me to build a building, the 327 building, which was designed and built in the 50s. At the same time, most of the other new buildings, 325, 326, 327, were three buildings that were all built at the same time in the 300 area. And at that place, why, we were examining sometimes as many as 2 fuel elements a month to find out why it had become defective. We established, designed, built. I had a great bunch of people there that were mechanical engineering from Oregon State, from WASU, Washington State, Lehigh, so forth, that did work in developing the equipment necessary to polish, to grind, polish, etch, and examine fuel elements. Beautiful job. So that constituted my life for about 15 years.
Marvelous.
Then I had a chance to go over and work at the plutonium recycle test reactor. So that's modern.
Yeah, well,
Were you able to make design improvements based on those examinations?
Well, most of the problems were connected with the weldments, where they enclosed the cans around the uranium. They would have leakers. The only other problem we had was when operations at the reactors would inadvertently or mistakenly not, they would block a tube so that water couldn't flow. And when that happens, the heat content would melt the aluminum. And so we would end up with fuel that partially corroded. It was not the fault of the fabrication of the fuel element at all. It was the operations of the reactor. And that only happened twice that I can remember. As I say, as I worked out at the visitor center next to the Energy Northwest power reactor, it's a 1,200 megawatt power reactor, I had people come out there to visit me that were very suspicious and suspect of radiation. And of course, that was one of the purposes of the visitor center, is to try to explain what radiation is all about. That it's dangerous, but we know what it is. We know how much we can tolerate. We can monitor it. And I had people that would come in there that I hope I convinced them that I had lived here since 44, and I was still alive and still going strong. What was the matter? What was the matter? What were they afraid of radiation about? The total claim was that they didn't know anything about it. That was the claim. And I try to explain that it's like fire. It can kill you or you can use it. Water, you can kill you or you can use it. Radiation, well, you got to be more careful because you can't see it. You got to measure it. So I always ask them, did they ever get sunburned? Oh, yes. Well, where did you think that sunburn came from? From radiation? Oh, yeah. So that gave them a little feel for radiation. But the terms that we use out here are very complicated. I think I have trouble with physics people who say that the fuel has burned out. And I've had people come in wanting to know whether it was like a lump of coal that had burned out. And I'd have to explain no. And in fact, we have an exhibit down at Crest that has an end reactor fuel element, and I let everybody pick it up. And I say, this is the way it looks when it went in, this is the way it is now, when it came out. It does not burn out. It burns out from a physics standpoint in that it does not produce any more heat or does not produce the right quality of plutonium. So the physics people, I try to convince them not to use the term burnout, because people, when you say burn, they relate it to trash.
so anything further you want to say about your experience in the Manhattan Project and how that?
Well,
should think
if
about
I've
that.
said it once, I've said it 1,000 times. I'm so impressed with the whole Manhattan Project. In January, I was lucky enough to be allowed to go into B reactor. And I keep thinking, here these guys were using slide rules, Marchant calculators, and DuPont, the genius in making it, having a safety factor large enough to make it work. Fantastic. I'm impressed every time I look at that face of the B reactor. It was 50 years ago that I walked through there, and it is fascinating to think that our minds of somebody could put that all together, and that we had construction people around here that could put it together. I remember going over to the graphite shop, which was near White Bluffs. That's when I was in my Blue Goose days. And they were machining graphite over there, and they were told that they could only use certain kinds of mouthwash. Oh my gosh, what's the matter? Well, certain mouthwash has poisons as far as the neutron is concerned. So they were given instructions there to use only certain kinds of mouthwash, so that they wouldn't spit on the floor or on the graphite. I think that particular machining operation is long gone, but they were, I like to kid people. I'm in a little skit down at Crest. I say, what are you guys doing, making pencils out there with all that graphite going in there? And of course, another guy playing a scientist says, I can't tell you that, I can't answer that question. Then you ask him a question, well, gee whiz, I have a little kid that told me that all you make is toilet paper out there. Is that true? Well, how'd you find that out? Well, my dad, all he brings home from work is toilet paper in his lunchbox. Stories.